Hi, we are Group 1. Fractionation process of fatty alcohol has been selected by our group as our topic for Chemical Process Control Module Assignment 2. This presentation covers the background of the fatty alcohol industry, the brief introduction of fractionation process of fatty alcohol, and as well the process control that has been proposed for the three major equipment.
Here I will present the background of the fatty alcohol in production industry. Firstly, the uses. All the industries get its natural fatty alcohols by converting the fatty acids in natural, like palm oil, into fatty alcohol by using hydrogenation process. Fatty alcohol has many uses in industrial production, like surfactants, which the 80% of its production is shampoo and lubricants in polymer process. Moreover, fatty alcohol can be used to produce emulsifying agents, which are substances that are soluble in both fat and water and enable fat to be uniformly dispersed in water as an emulsion. Foods that consist of such emulsions include butter, margarine, salad dressings, mayonnaise, and ice cream. Stabilizers maintain emulsions in a stable form. Emulsifying agents are also used backing to aid the smooth incorporation of fat into the dough and to keep the crumb soft. Alcohol can be separated into two types: the natural fatty alcohol and the synthetic fatty alcohol. The natural fatty alcohol is mainly produced using this method: hydrogenation of fatty methyl esters and direct hydrogenation of fatty acids. In our selected industry, direct hydrogenation of fatty acid is used.
Fractionation of fatty alcohols. Fractionation is the process by which mixtures of fatty acid are separated to obtain fractional purities up to 99.5% for products like fatty alcohols, methyl esters of fatty acids, and other organic compounds. Fractionation column system consists of deaerator, fractionation column, heating system, condensing system, and vacuum system. Fatty acids are heated using falling film evaporator. Falling film evaporators allow fatty acid to be evaporated gently and ensure low residence time. Fatty acid fractionated in packed column are equipped with structured packing to allow high separation efficiency and low pressure drop. The fatty acid vapor is condensed using surface condenser and steam generator for heat recovery. Importance of fatty alcohols and fractionation process. As a primary raw material for surfactants, fatty alcohols' growth parallels increasing economic prosperity and improvement in the standard of living. Fatty alcohols are increasingly gaining favor because of their biodegradability as well as availability from renewable resources. The world is in favor of natural fatty alcohols, and this can be attributed to the increasing supply and price stability of the lauric oil. The design process employed optimizes the recovery of heat and provides the highest quality of product available in the market today. The feedstock utilized in this process is distilled fatty acids. Vacuum towers equipped with structured packing are utilized to fractionate the fatty acids. Purities that are achieved via this process are approximately 99.5% for a C12 fraction from coconut fatty acid. With market demand for oleic acids and stearic acids, the process of fractionation in packed columns is gaining in importance. The packing provided in the columns has a very high efficiency with a low pressure drop and is used to achieve purities above 99%, especially for long-chain fatty acid fractions without any thermal damage to the final product. Distillation column is chosen as the major equipment because the process whereby fatty acids are separated into fatty acid fractions or individual components occurs in this column.
The first major equipment in this fractionation process is the fractionating column X7C005. The fractionating column X7C005 is marked in a red box in this P&ID. The feed of this fractionating column is a mixture of different types of fatty alcohol, which is generated through the hydrogenation process of the fatty acid. This is the zoom-in diagram for the fractionating column. The operating temperature of this column is 259 degrees Celsius and the operating pressure is 0.03 bar. The function of this fractionating column is to separate out the C6 to C12 fatty alcohol from the rest of the fatty alcohol. The chemical name for the C6 to C12 fatty alcohol is shown in the table below. In order to optimize the system, a total of two controls is proposed. The first control objective is to maintain the temperature inside the fractionating column. Maintain temperature is critical in the fractionating column because temperature will directly affect the efficiency of the fractionating column. If the temperature is too high, the unwanted component will be vaporized and exit as distillate. If the temperature is too low, the light key component will not vaporize fully and will remain as liquid form, which exit as the bottom. For this control objective, the control variable is the temperature in the fractionating column. The manipulated variable is the high pressure steam inlet flow rate, and the disturbance variable are the heat loss from the column to the surrounding, the inlet stream temperature, and as well the fluctuation of high pressure steam inlet flow rate. In order to achieve this control objective, a cascade control is proposed. In this case, the master loop will be the temperature control loop, and the flow rate control loop will be the slave loop. This is because the temperature control process is relatively slower compared to the flow rate control process in the high pressure steam inlet. Through the use of this cascade control, the disturbance in the high pressure steam and the inlet stream can be absorbed. The second control objective is to maintain the reflux ratio in the optimum value. Through the use of the optimum reflux ratio, the fractionating column can achieve the highest efficiency. For this control objective, the control variable is the reflux ratio, the manipulated variable is the reflux stream flow rate, and the disturbance variable is the inlet stream flow rate and the pressure inside the column. In order to achieve this control objective, a ratio control is proposed. The set point is first input into the ratio station, and the ratio station will calculate the reflux ratio and adjust the reflux stream flow rate according to the distillate flow rate. In this section, the advantage and practicality for both cascade control and ratio control will be discussed. The cascade control will be able to provide a faster response compared to the feedback control. With this faster response, the amount of off-spec product can be reduced, which will directly increase the profit of the industry. Besides that, through the use of this cascade control, the disturbance on both the column and the high pressure steam inlet can be eliminated. As for the ratio control helps to maintain the reflux ratio on the optimum point. Through the use of this optimum reflux ratio, the fractionating column will be able to achieve the highest efficiency. As shown in this diagram is the PFD drawn by using Microsoft Visual. Both ratio control and cascade control is drawn in this diagram as well.
In this section, I will be explaining the function of fractionation column X7C002 and how the proposed process control system achieve the control objective. As shown in the PNID, the feed of this fractionation column X7C002 is a mixture of different fatty alcohol, which is from the bottom stream of fractionation column X7C005 after the extraction process of C6 to C12 fatty acid alcohol, while the overhead desired product is myristyl alcohol and the bottom product consists of unwanted fatty alcohol. The function of this column is to extract myristyl alcohol from the mixture of fatty alcohol. However, there is no process control system to maximize the extraction process of myristyl alcohol. In this context, a feedback process control system will be proposed to maximize the extraction of myristyl alcohol from the feed stream. This process control system consists of composition analyzer, composition controller, and a control valve. The manipulated control and disturbance variable are identified before we proceed to the explanation on how the feedback process control maximizes the extraction of myristyl alcohol. The control variable for this feedback control system is composition of myristyl alcohol in the distillate. Manipulated variable is reflux flow rate, and the disturbance variable will be inlet feed composition. So, in order to maximize the extraction of myristyl alcohol from the feed, the composition of myristyl alcohol in the distillate is measured by the composition analyzer and compare it with the desired set point. The resulted error signal transmits as an electronic signal to the electronic feedback controller to be amplified. The controller output signal is an electronic signal that is sent to a current to pressure transducer, where it is converted to an equivalent pneumatic signal that is compatible with the control valve to make the necessary correction. If the sensor detects low concentration of myristyl alcohol in the distillate, the control valve will be open to increase the reflux flow rate or vice versa. The reflux flow back to the fractionation column for further fractionation process to obtain a higher composition of myristyl alcohol in the distillate. The advantage of the feedback control system is the corrective action occurs regardless of the source of disturbance. It is also more economical because less sensor is used since disturbance is not a concern. Feedback control can be applied even with limited knowledge about the process. For example, a process model is not necessary.
There are a lot of major equipments that can be found in a fractionation process. One of the major equipment is distillation column X7C004. Based on the PNID shown, the red color box indicated that distillation column X7C004. The feed of this distillation column is from outlet stream of X7C002, which is a mixture of fatty alcohol composition. The basic function of distillation column is to separate the desired product from the mixture based on the boiling point of the desired product. So that in this distillation column, the desired product that wanted to separate from the mixture is C16 fatty alcohol, which called cetyl alcohol. In order to separate the cetyl alcohol, the operating temperature of the distillation column should be same as the boiling point of cetyl alcohol. In this case, the cetyl alcohol's boiling point is 344 degrees Celsius. So that the operating temperature of the distillation column should be 344 degrees Celsius in order to separate the cetyl alcohol from the mixture. And the operating pressure is 0.03 bar. The lower the pressure will reduce the boiling point of the light key component, which directly affect the utility cost. Next is control objective. The objective of control system is to maintain the operating temperature of the distillation column. This is very important because the efficiency of the distillation column depends on the temperature. Higher temperature will end up in vaporize unwanted impurities into distillate product, so that the desired component in distillate product will mixed up with impurities. In other case, if the temperature is lower, will cause the desired product to not fully vaporize, which remains in liquid form and exit as bottom product, so that the amount of distillate product will be decreased. Analysis of process control. In this case, there are three variables that are identified, which is manipulated, disturbance, and control variable. The control variable in this case is the operating temperature of the distillation column X7 C004. Manipulated variable is the amount of steam inlet at reboiler, and the disturbance is amount of heat loss to surrounding. Proposed process control. To achieve the control objective, feedback control system is proposed for this case. This is because it will only take control action after the process variable and disturbance affect the process as well. Moreover, it is cheaper and simple control system. It is also more effective compared to other control systems. The PFT diagram as shown below is a feedback control system which is drawn by using Microsoft Visio. Practicality and advantage of process control. There are some advantage of feedback system. One of the advantage is corrective action will take place regardless of source and type of disturbance. It only needs little knowledge about the process to access it. Moreover, feedback system is versatile and robust, and it will increase the efficiency of the system.